During week 1 of this experiment, you will initially titrate a solution of picric acid with standardized sodium hydroxide to create a solution of sodium picrate of known concentration. You will then determine how much sodium picrate is extracted into a solution of methylene chloride containing a known concentration of crown ether. This is completed by vigorously mixing equal volumes of the sodium picrate solution and the crown ether solution. This extraction will be measured using UV spectrometry. For the second week of this experiment, you will submit to your TA an experimental procedure for comparing the extraction of each of the alkali metals using the same methylene chloride solution of crown ether. Your final report will include the standard lab notebook requirements, experimental data, and discussion of your experimentally measured results. Consider the reaction between octyl bromide and sodium cyanide, with these reactants in different phases. The octyl bromide is dissolved in an organic phase, whereas the sodium cyanide is dissolved in an aqueous phase. The experimental rule of thumb of like dissolves like would predict that the organic and aqueous phases are mutually immiscible. So if these two reactants can't mix with each other because of a lack of miscibility, how do they react? Unless vigorously mixed, this reaction will occur at a very slow rate. To increase the contact of octyl bromide molecules with sodium cyanide, a stir bar can be added to the reaction mixture and a magnetic stir used to vigorously mix the two immiscible layers. This effectively increases contact of octyl bromide with sodium cyanide and in turn increases the rate of the reaction. A phase transport catalyst, or PTC, must be able to transport an ionic species into a nonpolar organic phase. In the reaction involving octyl bromide and sodium cyanide, a PTC would transport the cyanide anion into the organic phase. A phase transport catalyst is not consumed in a reaction and can migrate back and forth between the two phases. A PTC should contain both polar and nonpolar characteristics and not be limited to liquid-liquid transfers. A typical quaternary ammonium or phosphonium salt would contain 4 organic groups containing 13 or more carbon atoms, which would facilitate solubility in an organic solvent. These salts are soluble in an aqueous medium and can associate with an anion, so the entire resulting complex can migrate into the organic phase. Due to the size of the organic groups on the quaternary cation, the anion is loosely bound to the cation and can dissociate and react quickly when in the organic phase. Any unreacted anion, as well as the PTC, returns to the aqueous phase. If quaternary ammonium or phosphonium salts transport anions, how are cations carried from an aqueous phase into an organic one? The structural requirements of a PTC for a cation are still the same. It must have both polar and nonpolar characteristics. PTCs that are effective for cations are compounds that are multidentate and macrocyclic. Multidentate simply means that 2 or more Lewis base sites are present on the molecule, with atoms of nitrogen, oxygen, or sulfur present as these base sites. Macrocyclic denotes a ring or rings composed of a relatively large number of atoms. Pictured here are several molecules suitable as PTCs for cations. The ring size and type of Lewis base site determines the effectiveness of a molecule as a phase transport catalyst. 2 naturally occurring substances that are phase transport catalysts are valinomycin and nonactin. Note the prevalence of base sites, or oxygen atoms, in the interior of the macrocyclic ring in both molecules. When either of these molecules binds to a cation, the conformation of the PTC changes. Conformational change results from a change in spatial arrangement of the atoms in a molecule, typically due to the rotation about individual single bonds. The size and basicity of each phase transport catalyst can determine the affinity a PTC has for specific cations. In this case, both valinomycin and nonactin prefer potassium ion over sodium ion. Each of these substances is responsible for transporting potassium ions across lipid membranes. The phase transport catalyst used in this experiment is 18-Crown-6, a crown ether. There are 18 atoms in this cyclic molecule, with the CH2CH2O grouping of atoms repeating 6 times. This molecule is depicted below on the left in a ball and stick model, and on the right in a space-filling model. In these models, oxygen atoms are depicted in red, carbon in gray, and hydrogen in white. The electron-rich interior of this crown ether results from the presence of basic oxygen atoms, allowing this molecule to associate with cations to form a complex in the aqueous phase. The hydrophobic exterior of 18-Crown-6 promotes solubility in an organic solvent and allows the crown ether cation complex, after forming an ion pair with an anion, to migrate from an aqueous phase to an organic one. During week 1 of this experiment, you will determine the ability of 18-Crown-6 to transport sodium ion from the aqueous to the organic phase. Picric acid is a strong acid and is yellow in color when dissolved in water. The phenol group can be titrated with sodium hydroxide due to the presence of the acidic proton on the OH group. This titrated solution provides 2 ions, the sodium cation to form the complex with the crown ether, and the picrate anion to form the ion pair. This ion pair can then migrate to the organic phase. The strong yellow color of the picrate anion allows a measurement to determine how much of this ion pair migrates to the organic phase. A known volume of picric acid solution is titrated with standardized sodium hydroxide to an endpoint of pH 7 to 8. This titration converts the sample of picric acid into a solution of sodium picrate. This titrated mixture is then diluted using a volumetric flask and the concentration of sodium picrate calculated. This solution is called the stock solution of sodium picrate. A measured volume of this stock solution is then diluted using a second volumetric to create the working solution of sodium picrate. It is this working solution of sodium picrate that is mixed with a methylene chloride solution of 18-Crown-6. Both picric acid and the picrate anion are brightly colored with a lambda max at 355 nanometer. It is this wavelength that is used to measure the concentration of the picrate anion. The sodium ion reacts in a 1-to-1 ratio with 18-Crown-6, and then this complex migrates with the picrate anion from the aqueous to the methylene chloride phase. After a period of vigorous mixing, the absorbance at 355 nanometer of picrate in the aqueous phase decreases due to the migration of the ion pair from the aqueous to the methylene chloride phase. By measuring the absorbance of the aqueous phase both before mixing and then after mixing, a quantitative measure of the transporting ability of 18-Crown-6 can be determined. Since only absorbance readings are needed to determine the effectiveness of 18-Crown-6, concentrations of any of these solutions are not required. This experiment is completed in pairs due to the limited number of pH meters. You will have to use your student ID to check out a burette and 2 100 ml volumetric flasks. Your working sodium picrate solution should have an absorbance of about 1.3 at 335 nanometer. Keep your procedure detailed and record all your observations. All absorbance readings in the UV-Vis spectrometer are taken without using any computer program. Your cuvette containing the aqueous sample is placed in the sample compartment of the spectrometer, and the absorbance reading is displayed on the instrument's screen. Your goal during the second week of this lab will be to extend your work of the first week by comparing the effectiveness of 18-Crown-6 in transporting all 5 alkali metals, or Group 1 elements. Each student pair will submit a written procedure based on your first week's work and submit it to your TA 24 hours prior to the start of the second week's lab section. Your TA may make suggestions to change your procedure, which must be done prior to starting the second week of this lab. All of the metal picrate solutions will be prepared for you, so you will not have to prepare them by titration. You will keep your working sodium picrate solution so it will be available the second week if needed.